Hello everyone, we are back. I am back for this particular chapter, that is Principle of Mathematical Induction. We'll be studying the second lecture. In last lecture we started with the introduction. What do you mean by inductive reasoning and what do you mean by deductive reasoning? So over here in this chapter we will be using inductive reasoning. What is inductive reasoning? We'll revise that. Inductive reasoning works in the way moving from we have some specific observations and using that specific observation we will prove it for generalizations and theory. Okay, so in last case we started with we mentioned one example, that is I explained using that example, that is Sn is equals to n into n plus 1 by 2, that we will be requiring induction steps to prove that Sn equals to n into n plus 1 by 2 is a general statement, because we cannot say if it is true for 1, 2, 3 and so on, so it will be true further also. So over there we proved that if it is true for 1, 2, 3 and so on, then it will be true for m, and if it is true for m, using that if it is true for m, we have proved that it is true for m plus 1. So you can start with we are starting with the theory part, which we left in the last class. So this is the statement which you can write for that particular example. Thus, if statement happens to be true for some particular values, it will be wrong to conclude that it will be true for all values. So there we require, that is principle of method of mathematical induction. So over here, method of mathematical induction helps us to move from a particular statement to general statement. So what are the basic steps? Let Pn be the statement. If Pn is the statement, so what is the basic step? The first basic step is P1 is true, and it is called basic step, that is simply a statement of fact. Now second statement is if Pm plus 1 Pm1 m plus 1 is true whenever Pm is true, Pm plus 1 is true whenever Pm is true. This particular step is called, inductive step, and it is a conditional property. So if the statement is true, for n equals to m, then it is also true for n equals to m plus 1. So by this we can generalize that Pn is true for all values of n. So this is the theory for it. You can write this particular this theory. So in last class we started with this. So why we require mathematical induction? Because even if some statement is given, it is true for some special cases, we cannot prove it true for each and every case. Thus, if a statement happens to be true for some particular values, it will be wrong to conclude that it will be true for all values. So we have this kind of a problem because we cannot say that it is true for all values. So the solution to this particular problem is mathematical induction. By using the method of mathematical induction, it helps us to form a particular statement, and using that particular statement, what we form is a general statement. Let Pn be the statement. So these are the steps. Let Pn be the statement if P1 is true, and it is called the basic step, which is obviously simply a statement of fact. Then if Pm plus 1 is true, whenever Pm is true, this step is called inductive step, and it is called a conditional property. So if the statement is true for n equals to m, then it is also true for n equals to m plus 1. By this we can generalize that Pn is true for all values of n. So let's start with some examples now. Let's take first example. Using mathematical induction, if n is prove that, using mathematical induction, prove that n is less than 2 power n for all values of, for all natural numbers. So the statement is Pn is a statement which is equals to n is less than 2 power n. Let's prove it. If it is P1, taking out the value of P1, that is 1 is less than 2, which is true. Taking second statement, that is P2, which is equals to 2 is less than 2 power square, that is 2 power 2, that is 4, which is again true. Now taking the statement for Pm is equals to 2 power m, m is less than 2 power m. Assuming if it is true, if Pm and which is equals to true, now multiply. What we can do is, next is multiply by 2 on both sides. So on the left hand side, what we have is 2m is less than 2 power m into 2. By solving this, what we have is m plus m is less than, it's m plus m is less than 2 power m plus 1. Now what is P of m plus 1? P of m plus 1 is equals to m plus 1 is less than 2 power m plus 1. Now we can see that now using first and using second, we can conclude that using first and second, we can say that m plus 1 would be either less than or equals to m plus m, and we know that m plus m is less than 2 power m plus 1. So over here we can say that m plus 1 is less than 2 power m plus 1. So we have proved that P of m plus 1 is also true. Now if P of m plus 1 is true, what we can conclude is, we can conclude that we can conclude that P of n is true for all natural numbers. So let's revise with the question. What is the statement that we are given? Using mathematical induction, prove that n is less than 2 power n for all natural numbers. Pn is equals to n less than 2 power n. Taking out value of P1 is equals to 1 is less than 2, which is true. Taking out the value of 2, P of 2 is less than 4, that is true. Now P of m is less than 2 power m, which is also true. Multiply now 2 on both sides. when we will multiply 2 on both sides, in LHS what we have is 2m. 2m is less than 2 power m into 2. 2 power m into 2 can be written as 2 power m plus 1. So in LHS what we have is m plus m. M plus m is less than 2 power m plus 1. Now putting the value of m plus 1 in the statement, what we get is m plus 1 is less than 2 power m plus 1. Now using the statements first and second, we know that m plus 1 would be less than equals to m plus m, and we know that using statement 1 we know that m plus m is less than 2 power m plus 1. So on the behalf of this, using this inequality, what we can conclude is m plus 1 is less than 2 power m plus 1. So it is true for m plus 1 also. P of m plus 1 is also true. So we can conclude that P of n is true for all natural numbers. So we'll start with second example. In second example, what we have is 1 square plus 2 square plus 3 square plus so on. N square is equals to n into n plus 1 into n to n plus 1 by 6. You have to prove it for all values of n belonging to natural numbers. Again, we will start with the basic step, that is Pn is equals to n into n plus 1 into 2n plus 1 by 6. We will prove it P1. P1 is 1 into 1 plus 1 into 2 plus 1 by 6, which is again equals to 1. So it is true for P1. Now we'll calculate it for Pm. Pm is equals to m into m plus 1 into 2m plus 1 upon 6. If obviously this is P of m is also true. Now using this, what we will add is m plus 1th term to it. When we add m plus 1th term to it, so what we are given is Pm plus 1 is equals to Pm plus m plus 1th term. And m plus 1th term is Pm is m into m plus 1 into 2m plus 1 by 6, and m plus 1th term is m plus 1. Now further solving it, taking out m plus 1 common, what we are left with is m into 2m plus 1 plus 6 into m plus 1, because we have taken out m plus 1 as common and even taken the LCM. So on further solving it, what we are left with is it is 2m square plus m plus 6m plus 6 upon 6. So it is m plus 1 2m square plus 7m plus 6 upon 6. Now we will take out 6 again common. So what we are left with is m plus 1 by 6, and inside the bracket what we are left with is 2m square plus 7m plus 6. If I will further split it, 6 into 2 is 12, which can be further splitted as 3 into 4, and we know that 3m plus 4m is equals to 7m. So by splitting the middle term, what we will get next is m plus 1 by 6 into 2m square plus 4m plus 3m plus 6. Further solving it, m plus 1 by 6, 2m, m plus 2 plus 3, m plus 2, and so on. Now m plus 1 by 6 we already have. What we next have is m plus 1 into 2m plus 3. Now if we can see, what we can see is, what we have a formula for Pn. The formula for Pn is n into n plus 1 into 2n plus 3. So if I further solve it, if I further manipulate it, can it be written as m plus 1 into m plus 1 into 2 into m plus 1 plus 1, because 3 can be written as 2 plus 1, and when we will club 2m with 2, what we are left with is 2 bracket m plus 1 upon 6. So it is m plus 1 into m plus 1 plus 1 into 2 of m plus 1 plus 1 upon 6. So we can see that this will act as n here, and this will act as n plus 1, and this will be written as n plus 2n plus 1, which is same as the statement that we have used previously, that is Pn is equals to n into n plus 1 into 2n plus 1. If it is true for, so if it is true for P of m plus 1 is true, and if P of m plus 1 is true, hence it is true for all values of n belonging to natural numbers. So let's start with the initially what we did in this lecture is, let's revise. We started what I had explained in the last class. We are just writing the theory for it, that it is not possible that if you can prove that P of if there is any statement Pn and you are proving it correct for n equals to 1, n equals to 2, n equals to 3, it is impossible, and it is very tedious work to prove it for each and every natural number. So if we cannot prove it for each and every natural numbers, we cannot generalize that. Thus, if the statement happens to be true for some particular values, it will be wrong to conclude that it will be true for all values. Method of mathematical induction. So in order to solve this problem, what we have is method of mathematical induction, so which helps us to prove it which helps us to move it from a particular statement to a general statement. If Pn be the statement, if P1 is true, then it is called basic step, and simply a statement of fact. We can prove Pm plus 1 is true using that Pm is true. So first, if the statement is true for n equals to m, then it is also true for n equals to m plus 1. By this, we can generate that Pn is true for all values of n. Using the mathematical induction, prove that n is less than 2 power n for all natural numbers. Pn is equals to n less than 2 power n. If P of 1 is less than 2, which is true. P of 2 is less than 2 power 2, which is 4, which is also true. Now we have proved that P of m will be true. M is less than 2 raised to power m. Now multiply 2 on both the sides. What we will get is 2m is less than 2 power m plus 1. 2m can be further split into two values, that is m plus m is less than 2 power m plus 1. Now if m plus m will be obviously greater than or equal to m plus 1. So using the equations first and second, what we can see is m plus 1 is less than equals to m plus m, and that is less than 2 power m plus 1. So using this particular combined inequality, what we can see is m plus 1 is less than 2 power m plus 1. So P of m plus 1 is true. From that we can conclude that it will be true for P of n for all natural numbers. Similarly, next example what we had is 1 square, 2 square plus 3 square till n square. We had a general formula for it, that is n into n plus 1 into 2n plus 1 by 6. We have proved it true for n equals to 1. We have proved it true for n equals to m, and using P of m is true, we have proved it that it is true for P m plus 1. Because if we will add m plus 1th term in Pm, what we will get is P of m plus 1, and we can see that it is following the same rule that we have mentioned above, that is Pn is equals to n into n plus 1 into 2n plus 1 by 6. So it is also following the same rule, and if it is true for Pm plus 1, using Pm is true, and it is true for all values of n belonging to n. So that is all what we have in this particular chapter, that is mathematical induction, where we are trying to use inductive theory. We are starting from specific values, from some specific values, and using those specific we are trying to generalize things, and we are using this particular two-step theory where we are proving it true for P equals to 1, that is a basic step, and then using that Pm is true, we are proving that P of m plus 1 is true. So using that we are proving it further that it is true for all values of n, and this particular step is known as inductive step. Thank you, and that is all for this particular chapter. I hope you can do the exercise of your NCERT, and that will be all. Thank you.